Hello, in this video we're going to finish the proofs that the symmetric group is a group. This is mostly going over and reviewing some proofs about functions from Math 3350. So if you remember those facts that were mentioned in the previous video, you can skip this video. If you don't remember the proofs, you probably should watch this video. Alright, so this was the claim we had. The symmetric group is the set of all bijections from a fixed set to itself. And we claimed it's a group under composition. And one of the first properties we needed was closure. So what do we want to show? Given any two permutations, we want to show their composition is also a permutation. So what does it mean to be a bijection or a permutation? It means that it's injective. So that's one part we're going to need. This is a thought bubble, by the way. We're not quite there yet. It's just thinking what we need to do. What else do we need to show? We need to show it's surjective. So how do you show something is injective again? Well, you need to take two elements in the set X. You're going to suppose they have the same function value under your function. Do a little dance, make a little proof, conclude that they were the same element to begin with, and then you've managed to show that it's injective. Now, how do you show something is surjective? Well, you take an arbitrary y value, engage in some black magic and some summoning, pull a rabbit out of a hat, and find a particular x value with the property that sigma composed with tau of x is equal to y. And then that's all you need to do. So first we show sigma composed with tau is injective. We let x and y be elements of x, and we suppose that they are mapped to the same function value under this function. Well, what's the definition of composition? It's sigma applied to tau of x and sigma applied to tau of y. So these two are equal. All right, well, since sigma is a bijection, sigma is injective. And so in particular, sigma maps tau of x and tau of y to the same value. And therefore, tau of x must be equal to tau of y. Sometimes I illustrate this with pictures, so let's actually try to do that right now. So I don't know what x and y looked like at first. We know that they were mapped to tau of x and tau of y. And we know that in sigma, we end up with the same point. And the point is, because we're injective, sigma is injective, that tells us that these 2 points actually had to be the same. So we drew the picture wrongly. You must actually have this picture. And that's one way to think about injectivity, is that this picture doesn't happen. So that's what you're doing. You're assuming that it looks like you might have this picture and then actually proving that these 2 points are actually the same point. And, you know, it's like sometimes when you're talking to a friend and you're talking about someone, and it turns out you both discover you're talking about the same person. Not that I'm advocating for gossip. So now we see tau of x is equal to tau of y. Since tau is a bijection, and that means tau is injective, since tau of x equals tau of y, it follows that since tau is injective, x equals y. Congratulations. you had made the same confusion twice. X and Y were actually the same point to begin with. Oh, and that's exactly the point we wanted to make. Therefore, if the function composition sends x and y to the same value, then x and y were the same value to begin with. Hence, sigma composed with tau is injective. Notice this actually tells you the fact that we normally state in Math 3350, if sigma and tau are injective, then so is their composition. And the way that argument is actually set up, these functions don't all have to have the same domain and codomain either. Now we claim that sigma composed with tau is surjective. So we want, oh, I should have used y here. So let's edit as we go. We've got some y value way over here, and we want to be able to get to it by sigma composed with tau. Well, because sigma is surjective, yeah, I'll stick with what I currently have and just call it x. So we got some element in the codomain, and we want to be able to find something that maps to it. The idea that we're going to use is that under sigma, we can find an element that maps to it because sigma is surjective, because sigma is a bijection. I mean, that doesn't tell us how to get to the composition yet, but we have two functions going on, so because tau is surjective, we know that there's some point in x such that tau maps z to y. And so, since sigma is surjective, x equals sigma y for some y in x. Since tau is a bijection, tau is surjective, so y equals t of z for some z. Then sigma composed with tau applied to z is sigma of tau of z, which is sigma of y, which is x. And we're just pointing out what you actually see. Z goes to y goes to x, therefore under composition, z goes to x, and look, you found an element that maps to x. And that's what we want to show. Hence, sigma composed with tau is surjective. For any point x in the codomain, there exists a point in the domain that is mapped to it. Since our composition is injective and surjective, it is a bijection, and therefore it is in the symmetric group. Another fact we assumed in the previous video, in the proof of associativity, is that for any three bijections, we had this equality. Let's actually do the calculation. Sometimes it's given of us a homework problem in the 3350 textbook, but it's almost never assigned, so it's probably worth seeing it for once in your life. Since the domain and codomain of all these functions is x, you can check that the domain and codomain of this double composition on both sides is x. So the only thing you need to check is that given any element in x, the value under this function is the same as the value under this function. By the way, this funny symbol is called rho. So let sigma, tau, and rho be bijections, and let x be an element in our set. Then let's compute what happens under this double composition. Well, by definition, this composition symbol is given by applying sigma composed with tau to the value of rho of x. Well, what's sigma composed with tau? It's computed by applying sigma to tau of this number or element, which is rho of x. So we have sigma, tau, rho. It turns out, oddly enough, the same thing happens when you look at this calculation. By definition of composition, this calculation is just sigma applied to the value tau of rho of x. But by definition of composition, tau of rho applied to x is just tau applied to rho of x. And look, it's literally the exact same expression. Therefore, these two quantities are equal. And since they're equal for any x, the two functions are equal, and therefore composition is associative. And now we get to one of the big theorems from the 3350 course. A function is a bijection if and only if there exists an inverse, a function g from b to a that satisfies these two properties. Remember, we use this to prove that there are inverses in the symmetric group. So remember, there's an if and only if. So that means that the proof has to have two directions. So in one of the directions, we're going to assume that you have a bijection, and then prove that this function exists and has these properties. And then in the other direction, we're going to do the reverse. We're going to assume this inverse exists and then prove you have a bijection. Now, usually with existential quantifiers, it means you have to figure out what the right definition is for G. And here I already gave it. So the idea, of course, is, well, let's just do it by example. And to make it more interesting, I'm not going to use 1, 2, 3 for the codomain. Let's send 1 to C, 3 to A, and 2 to B. So there's my F. So the point is, you want a function such that when you do the composition, you get the identity back. Let's focus on this side. So F sends 1 to C. I want to figure out where to send C so that when I do F composed with G, I get back to 1. So F composed with G of 1 should be 1. So if 1 goes to C, C has to go back to 1. Literally, the inverse is computed by reversing the arrow directions. So C goes to 1, B goes to 2, and A goes to 3. That's the definition of the inverse. And then you quite see, since 1 goes to C, C has to go back to 1. 2 goes to B, B goes back to 2, 3 goes to A goes back to 3. So if you do the composition either order, you do get the identity. Of course, proof by example never counts in mathematics, so let's explain what this reverse the arrow construction actually means. So what are you doing? You're taking this point, since F is surjective, given an element in this codomain, we know it's the end point of one of these arrows. In other words, there exists an A such that this arrow exists. There exists an A such that F of A is equal to B. Reverse the direction. Define G of B to be A. I'm using this little subscript B here because later this is actually relevant to point out that our choice here was made right now. That for every B in our codomain, we're making a specific choice because we know there exists at least one. And then we're using that to define this function. We're not saying anything about whether or not there's more than one. We're only using surjectivity here. And so there was a choice to be made. It turns out there's only one, so that choice is unique, but that requires injectivity as well. So we have a function. For every B we've defined it in A. It's called reverse the arrow. Now we just need to show this composition is the identity. We'll let B be an element in this codomain set, B. Then F composed with G is just F applied to G of B. We define G of B to be this special element in A with the property that F maps it to B. So F of G of B is F of A sub B is F is B. By definition, by construction, by design. So guess what? You plug in B, you get B back. F composed with G is the identity. So far we haven't used injectivity, so this construction works for surjective functions. We use injectivity here. Now we need to show composition the other direction. Let A be an element of A. Then F of A is equal to B for some element in B. And we know G composed with f of A is this element AB, A sub B. So here's where the subscript is important, because the point is for every element in B, we made this choice. But right now, I took an arbitrary element of A, I plugged it into this equation, I got some answer, and then now I'm getting a different x value, so to speak. So the point is, it's not entirely obvious that A, B, and A are the same yet, because this was something I chose well in advance, and this is something I'm choosing right now. So by definition, f of A sub B is defined to be B, which is the y value of f of A. So in particular, f maps this point and this point to the same value. But since f is injective, that means these 2 points were actually the same. So all this fussing about subscripts turns out not to matter. So why do I worry about it? Because if this wasn't a bijection and only a surjection, you can actually still construct this function, and you actually still get this composition, but this one fails. So that's an example where you get an inverse on one side but not the other. But we only care about bijections in this class, so look, we have an inverse both ways. Now we need to prove the other direction on an if and only if statement. Suppose that we have an inverse. I'm going to write these equations as 1 because we're going to use it. Suppose we found a function from B to A such that these two equations hold. We want to prove that f is a bijection. So we need to show it's surjective and injective. Apparently I decided to do surjectivity first, probably to match what I did on the previous part. So the previous part, the first composition identity followed from surjectivity, the other composition identity followed from injectivity. And now I'm mirroring it so that you can see the exact relationship. So let's prove surjectivity first. We want to prove f is surjective, so let's take an element in B. We need to find some element in A that maps to it. Well, I mean, we have this nice construction about reversing arrows, so why not choose A to be G of B? Well, then what's f composed of G of B going to be? What's f of G of B? G of B is A, so that's f of A. But because of this identity, that's also equal to B. So f of A equals B. So we found a point in our domain that maps to our given point in our codomain. So every point in our codomain has an element in its pre-image. So f is surjective. Well, now let's prove injectivity. Let A and A prime be in the domain. Suppose they're mapped to the same point under this function. Compose on both sides with G. Since G composed with F is the identity function, that means that A is equal to G composed with F of A, which is equal to G composed with F of A prime, which is equal to A prime. So A is equal to A prime. Congratulations, you're injective. So now we see this equivalence of these two definitions. A function is a bijection if and only if it has an inverse. And this is actually sometimes useful. When I teach the proof writing course, I point out that in my area of mathematics, oftentimes the way we define a bijection is by giving its inverse and proving this, instead of doing surjectivity and injectivity. Although, as we'll see in this course, when you're dealing with groups and rings, there's actually other ways to prove injectivity anyways.